Today, we're going to do some satellites, like satellites going around the Earth. This is going to be our first practice problem that we do. It's like a Sputnik, it's just has a purpose. Sputnik didn't have purpose. I'm going to draw the Earth. It's a little lumpy, but there's the Earth. And we're going to put like a little satellite up here. Doop, like that. Little solar panels out to the side. Looks good. And this satellite is going to be special. This is going to be a television satellite. And the thing about televisions or cell phone satellites or things like that is you don't want the satellite to move away from the orbit above where it's actually servicing. So there's a couple of different ways to do this. Obviously, things that are in orbit are going to go around the Earth in a circle, but a lot of cell phones and communication satellites, the orbit, the orbital period, how long it takes to actually go around the Earth, is the same as it takes the Earth to revolve. So what ends up happening is this satellite just ends up beaming this information to a particular part of the world. There's Florida. So as the Earth spins around, this satellite is going to spin around at the exact same rate above it. So it just looks like the satellite is just like floating above us. Okay? That type of orbit is called a geosynchronous orbit. Geosynchronous. I hope I spelled that right, but if I didn't, that's okay. We're in AP Physics. We don't actually have to spell things. All right. We're going to put in, if it's geosynchronous, the period, the orbital period is going to be what? How long did it take this satellite to go around in a circle? Which is? The same time as always, which is what? Well, it's the same as which planet? Okay, and so the orbital period around Earth, if the Earth spins around once every, no, not even close, not even close. Yeah, no, 24 hours is what. Yeah, totally what I was aiming for. Yeah, so it's every 24 hours. We do need to change this to seconds, though. We do need to change this to seconds. I think it's 86,400. Right. I think that's 86,400. So remember, whenever we do these, it's the KMS system, so you need this in kilograms, meters, and seconds. So even though it says 24 hours, we need to change those hours over to seconds. Okay. Um, let's see here. I'm going to read this problem out. Broadcasting satellites are used in satellite television system orbits Earth's equator with a period of exactly 24 hours, the same as Earth's rotation period. As a result, these satellites are geostationary or in geosynchronous orbit. They always remain over the same spot on the equator so that they always appear to be in the same position in the sky as seen from the Earth's surface. At what distance from the Earth's center must a television satellite orbit? So we're looking for the distance. And then the second part is what must be its orbital speed? So we're looking for the distance. How high does this thing actually have to be above? So we can just call that distance d. Okay, now I have to be careful here because whenever I write this out and I say that this is the orbital distance d, yeah, erases everything. This distance is actually going to be the distance from the satellite to the center of the mass of the Earth. So this distance right here is going to be our total distance whenever we plug it into the equation. So we're going to need the value or whenever we find this distance, if you're looking for the height, how high above the Earth is it, we're going to have to subtract away the radius of the Earth so that we would get a true value. Okay? Because if you just give me the distance also includes the radius of the Earth as well. So if we want the height, we'll have to take away that number in order to find out what the actual one is. or that they're so far, yeah, or that they're so far away from each other. In the case of the Earth right here, we're going to have to worry about it. Okay, so what we're going to do is we're going to try to find the distance, d, or r in this case, and we also need to know what the velocity is. So we're looking for both of these things. We're looking for the distance, and we're looking for the velocity. And we're probably going to need a couple of tools under our belt to make this happen. The first thing that I'm thinking of is that we can use the force of gravity being equal to big G times little m times big M over the distance squared. I'm going to go ahead and call it d squared this time instead of r squared because I've got the variable d inside. But there's a small problem here. I don't have velocity, and I don't really have a weight of the satellite. But if you remember from yesterday, the weight or the mass of the satellite doesn't matter. Okay, it doesn't matter what we put up there. We could have put a cat up there. We could have put a satellite up there or a moon up there. It wouldn't have made any difference whatsoever between any of those. So GMM over D squared isn't gonna do it by itself. So what formula did we come up with yesterday that could try to help us out? And if you don't tell me, we're gonna have to rederive it. I will make you. Do what? There is an r cubed over t squared. Yes, that is true. That is true. Okay. So, and there's a 4 pi squared. And we just have to put all this together into one cohesive, coherent thing. So I heard t squared over r cubed. Okay, I heard r cubed over t squared. I'm going to try to erase this. It's not going to work. I should have restarted my computer, but I didn't. There we go. So r cubed over t squared. There was a what else? G big M over 4 pi squared like that. Okay, this thing is called the what? Yeah, this is the Keplerian constant. Okay, so as long as we know the mass of the Earth, which we can look up, that's a Googleable thing. It may not give it to us straight in the problem, but that one is an easy Googleable thingy madoober dab. And as long as we know the universal gravitational constant, we should be okay. What is it? I'm gonna write that. That's right, 5.97 times 10 to the 24th kilograms. We could have just gone with 6. I'd have just gone with 6. 5.97 is really close to 6, but I'm going to go with like 5.97 times 10 to the 24th. That'll give us a pretty accurate answer. All right. Do we know what pi is? We're okay on that part, right? Okay, good. Okay, as long as you give me 3.14, I think we'll be fine on that one. We need to find the radius. Do we have the time? The period? Okay, so actually it looks like we have everything on here except for one thing, right? So why don't we use this? This is totally a Kepler's third law problem. We just have to make sure that our calculators can handle this cubed and squared crap. I would highly recommend that you do not use a cell phone for this one. So r cubed over what's that period? 86,400 squared. Yeah, exactly. Try that in a cell phone. Actually, try these in a cell phone because the universal gravitational constant is super tiny. You just want me to write tiny in the equation? We can get away with it. Just write tiny here. Oh crap! No, I shouldn't have done that because now I can't erase it. There we go. You don't know what the radius of the Earth is? Wait a minute. Oh, we'll need that. We'll need that later. Let's just focus on this expression first. I need big G. That's what I need. Yeah, I need big G, the universal gravitational constant. Okay, 6.67 times 10 to the negative 11th. You want to write the units or just leave them? I had a feeling you would say that. It's okay. 6.67 times 10 to the negative 11th. It will. We proved yesterday that it would cancel out. Mass of the Earth, 5.97 times 10 to the 24th. 7 times 10 to the 24th kilograms. The bottom 4 pi squared. Okay, y'all just want to knock that out, or you want to try to solve for r cubed? What are you solving for? Okay, have at it. Have at it. I'll let you guys have at it. You are. You were trying to find r cubed. Yep. Try it out. I'll help you out. Coefficient of friction with the centripetal acceleration. Okay, so for that one, you know they're going to balance out. So whenever you've got a coefficient of kinetic friction, um, is it going in a circle and is it like staying still? Yeah, so like those are balanced. So the centripetal force is the force that's pulling it in, and the friction will keep it in place. So the frictional force is going to be equal to the centripetal force, which is mv squared over r. Okay, so you got to use Newton's second law for that one. I'm trusting you guys. I'm not working this one myself. So that means we're going to need an answer, and we're going to need a second for that. Mm. Does make a difference. Yeah, but you do have the AC. You do have the acceleration. And you could say that AC is equal to v squared over r. I don't think you necessarily, yeah, you don't necessarily need the mass. What even is cubed root? It's the inverse of the number times the number times the number. 42222. I need this in a number that's in English, please. What? You can say that. You got to say that number to me. Can you write it in exponential notation or scientific notation? That's what I meant to say. You're going to take this number and you're going to multiply it over the other side, and then you'll take the cubed root of it. So it's this times that squared divided by 4 pi squared, and then you got to take the cubed root. I would do it in chunks. I wouldn't do it all at once. If you try to do all of these calculations at the same time, you're going to go crazy. Trust me. I've already gone crazy on this one. Times 10. Okay, so times 10 to the 7th. Okay. Okay. 1, 2, 3, 4, 5, 6. Okay. I think y'all are starting to get the same answer all the way around. Mm-hmm. Me? Oh, no. I was like, what did she? Hmm. Are you trying to do the cubed root? Okay, you can cubed root in the calculator by doing this. This is the old school way, caret 1/3. So the 1/3 power is the same thing as the cubed root. It's probably an easier way to do it. The big thing, yeah, I think everybody's starting to get 4.2 times 10 to the 7th. So our radius value, once we do this calculation, so let's see, I'm going to just go ahead and put this up here. It's 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th times 86,400 squared. And if it was me doing it, I would put all that in the calculator first, hit enter, and then I would divide that by 4 pi squared, and then hit enter, and then I would take the square root of both sides. So I would go r cubed, goodbye, and then cubed root this, like that. There we go. Yeah. And that's 4.2 times 10 to the seventh meters. Okay, 4.2 times 10 to the seventh meters. Um, Fair. That is what we got. Okay, no. That's actually what it's supposed to be. The radius of the Earth is 6.37 times 10 to the third, or sorry, 6.37 times 10 to the sixth meters. It's 10 to the third kilometers. So let's go 10 to the sixth meters. So if the radius of the Earth is 6.37 times 10 to the sixth meters, this number for the radius of the satellite, let's call it RS, is actually that was a little r, wasn't it? Sorry. Let's go little r. That was 4.2 times 10 to the seventh. That's a bigger number, so that's good. That's a good way to double check ourselves and be like, okay, 4.2 times 10 to the seventh meters, that is a bigger number. How much bigger is this compared to the Earth's radius? How high do we actually have to put this? Because we live on the surface of the Earth, which is 6.37 times 10 to the 6 meters away from the core, the center of mass of the Earth. Which, by the way, if you're in the center of the mass of the Earth, you would just float. I don't know if that kind of hurts anybody's brain, but you'd also be like crispified, but yeah, it's not hollow in there, I promise. It is, yeah. They think that there's a metallic core inside, and I do believe that it is nickel, yeah, if I remember correctly. Yeah. So if we wanted to find that, we could say that we just subtract the two numbers. What? Well, yeah, if we subtract these two, but if you subtract them, if you subtract both of them, you shouldn't get a 10 to the seventh, though. I don't think. Really? I mean, like, I don't think so, but I could be wrong. I could be really wrong on that. Okay, never mind then. I'm wrong on that. So, what do we? It won't be the first time, and it won't be the last. So what was that value? So the height that we actually had to put in there, 3.6 times 10 to the seventh. Okay, fair. Meters, which is well above the radius of the Earth. Because if the radius of the Earth is only 6.37 million, then the distance that we're going to put it up there is somewhere around 36 million, or 3.6 times 10 to the seventh meters. So we're going way up there. That's about 6.63 times the Earth's radius. So we're going up quite a bit. Okay. How many kilometers is that? We would divide it by 1,000. So that's 3.6 times 10 to the fourth, which would be 36,000 kilometers, I think. Hang on, I gotta check that one. That's 3.6 times 10 to the fourth. So I would go 1, 2, 3, 4. That'd be 36,000 kilometers, yeah, which is quite a ways. Yes, that's correct. Yes, yeah. I don't know. All right, now how do we find the orbital speed? We got half of it down. Now we got to find the orbital speed. Orbital speed. That's velocity. We got to find the velocity. So we did something similar to it. Kind of. Yeah, we can use acceleration in this case because we know that acceleration is equal to v squared over r. Um, we know that this thing is going in a circle, right? So we know that as this thing is moving around in a circle, then we have a let's see. We know that we have the forces being balanced to each other. So the centripetal force is gravity. Kind of, except now we're dealing with like the actual planets though. So circle is circle. Yeah, so the gravity is the centripetal force. So what's the force of gravity? Negative. You are not on Earth right now, so you cannot use 9.8. Yeah, we're in space, so satellites in space. So we have to use GMM over R squared. So GMM over D squared. And the centripetal force is mv squared over R. Or I guess let's call it mv squared over D. How's that? There is hey, we've done this before. This is like deja vu all over again. Because I know that something happens. I'm getting my red pen ready. V squared over D. The V squared can be changed to something. Um, you're getting there. You're getting there. You're like halfway there. Okay, so like the velocity of something going around in a circle is distance over time, right? What's the what's the distance? So our velocity is there we go. It's the circumference of a circle. So it's circle over time, right? And the circle's distance is 2 pi r. So if we're going to square that, then we're going to have to rewrite that. I was kind of hoping that you guys would cancel the mass first rather than worry about the velocity. Thank you. Yeah, so I'm going to do that first. I'm going to cancel the masses out. Everybody brought mass to the party, so bye-bye. That should be your first thought, is to simplify rather than make things more complicated. Yeah, and then taking the v and moving it out, that is complicated. So the velocity is 2 pi r over t squared, and then divide it by the distance. Okay? Yes. Okay, the d is going to move up, right? We could actually cancel out one of these d's if we wanted to right now. Um, I do want to say one thing. I did make this overly complicated because this r is actually the distance d, right? So that would be 2 pi d squared. I'm just too used to writing it as r for radius. So let's go ahead and I'll fix that for right now. Okay, so that becomes, I'm going to start over here, 4 pi squared d squared over t squared d equals gm over d squared. Okay. Okay. One of those cancels. That's okay. Um, so that's 4 pi squared d over t squared equals g m over d squared. They don't cancel. Yeah, but like, can we combine them? Yes, because we can cross multiply, but they don't cancel. You cross multiply them, and the d and the d squared are going to become a d cubed. Now, do you want it in the top or the bottom? Top? Okay, you would rather prefer it that way. That's okay. So we're going to take the d squared and we're going to move it up then. So that's going to be 4 pi squared d cubed over t squared equals g m. And at some point, nah, I'm gonna wait. I'm gonna wait. The fruit is sweeter if you wait. Okay. Yes, this is a very good question. What are we trying to find? We are? We're trying to find velocity? If we're trying to find velocity, wait a minute. Well, wait a minute. Hang on. Like I need y'all to think about the path that we're going and how we got here. Because at some point you're going to start to realize that you've made a huge mistake in your life and that you're not even right. Do you know why we're doing this? No, because you told us to. Whoa, 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 whoa! I didn't do this. I didn't do this. You did this. Yes, you did. Yes, you did, and I have it recorded as evidence. Yes. Because whenever I was like, "Hey, here's the velocity," and y'all were like, it's 2 pi r over t." So I was like, "Okay, let's substitute it in." Guys, we were looking for this up here. Halfway, not completely. Yeah. Yeah, so every time like the microphone filters, so you'll hear it sounds like the Charlie Brown voice. So he's gonna be like, and it's fantastic. But I didn't do it. It wasn't me that did this. So can we use this expression? Absolutely. This is Kepler's law. Okay, so what we just did was we just rederived Kepler's law, which says that 4 pi squared d cubed over, hang on, I'm just write it all down, gm over 4 pi squared. This is the Keplerian constant. We basically just did Kepler's law again. What you're looking for this up here. You're looking for this. Okay, the masses cancel out. You have the distance. You have the mass of the Earth. You just need to solve for v. That's all you gotta do. Yes. Well, I mean, like, what do you mean, like, from over here? Hang on, hang on, hang on, hang on, hang on. We could also do that as well. That would work. Yeah, that would work as well too. Yeah, so you could do it this way, okay, and it would get you an answer for the velocity, and it would give you something. Or you could also use the 2 pi r over t. You have the radius that we just calculated from the last problem. We know that the time is 86,400 seconds. The answer from this solution, let's see if it actually highlights 2 pi r over time. This solution for velocity is the exact same answer as this solution for velocity. Either way is fine by me, okay? But this wild goose chase down here will only lead you to disappointment and sorrow, okay? So yeah, the radius of the Earth is 6.37 times 10 to the sixth meters. Okay, so it's 2 pi times, but don't use the radius of the Earth. Use the d that we found. The radius of the satellite, which is 4.2 times 10 to the seventh meters. Yeah, 2,617. It's a little slow. Little slow. Check and make sure. We are using the radius of the satellite, right? 4.2 times 10 to the seventh. 2 point, yeah, 2 pi times the radius of the satellite. 3054.32. That is a lot closer. Yeah, that is within the realms of a correct answer, quote unquote. 3,000 is roundabout what we're looking for. Okay. Now, it may be, hang on, it may be that this 2 pi over t. No, hang on. Think about this. Think about this. The time that it takes to go around the Earth isn't exactly 24 hours. There's a little bit of error associated with this answer. So it may be that the velocity just may be giving you a different answer for 2 pi over t, just a little bit different than the velocity over here, because we definitely know the mass of the Earth and the gravitational constant within a lot of significant digits. So that's okay. It's all good for you. Yeah, it is. It's all good for you. It's healthy. It's healthy that way. Now, if you want to know if y'all are the formula memorizers, if you solve this for v, then you can get that the velocity is equal to the square root of g m over, I think one of the d's cancels out, so that's gm over d. You could actually use this to calculate the velocity of something in orbit, and that would work every single time. As long as you know the mass of the planet and the radius, you're good to go. So you could use that one, and I would highly recommend that y'all at least commit that semi to memory, or at least commit how to get that to memory. Okay, that's okay. Yeah, this is fine. This is good. This is good conversation, to be honest. Okay. And I'm fine with that. And it's it's gonna warrant it because I do let y'all go down wild goose chases, and that's okay. This isn't the first time that we've done that. Okay. He does not. Oh, I figured not. Yeah, I wouldn't. Yeah, they're just like, no, this is the way. But I have to train you guys to be able to think differently because I cannot like whenever you take the AP Physics exam, those open response problems are like demon hybrid babies. So there's not like yeah, the chances of us going over a problem in class that is exactly like the open response is like slim to none because they're going to come up with some way to do something and it's going to be crazy and you have to be able to think your way through it. You have to say, "Oh, hey, this is circular motion. Oh, hey, gravity is equal to the centripetal force. Oh, hey, I can derive this." Okay? So like this is where the difference between a 3 and a 4 and a 4 and a 5 come in on the AP Physics test is your ability to think on your toes and to be able to come up with these solutions. And if I don't let you guys go down the different routes, I'm not teaching you guys how to do that. Okay? So, yeah, and that may happen to you guys on the AP Physics test too. You may go down the wrong route. That's okay. Back up and then go again. What happens if what? That can happen. It all depends on how the weighting of the scores runs out. It's half and half. So half of the weighting of the AP test is multiple choice, and the other half of the weighting is the open response. So if you that would yeah right it would definitely be a passing score even if like you just drooled on the open responses. Okay. But in my experience, it's actually really easy to get a 25 to 30% on the open responses easily without really trying to work too terribly hard. I've had people that they could not do math like at all. Like every time I started putting equations on the board, they're like, "This is crazy, Mr. Broadway. I don't even know what's going on." And they were in AP Physics and they made a 3 on the AP Physics test because on the open response they just killed it because they asked them to like you don't have to hang on, we just had a large student announcement. Yeah. Yeah, large student announcement there. Sorry about that. Okay. So, all right. You don't good old yeah, good old yeah, good old COVID. All right. So you don't have to the question was like you don't have to do math. That's wrong because you do have to do math to get on it because obviously yeah, but they explained it in ways that didn't involve like they kind of skirted around the math and they got as much partial credit as they could and they actually ended up passing the AP Physics exam by explaining as much as they could. But when it came to like derive the expression, they were just like, "Nah, bro," and then that was it. They just skipped it and they moved on. Okay. Do what? Can't. Yeah, right. So I don't. It's just that way. No, don't flex on them. Don't flex on the judges. It's generally not a. Do not flex on your graders. Yeah, do not flex on your graders. No, 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 no. You do have to show your work. Yeah, you can't just write an answer and be done with it. You do have to show your work. Okay. Now, I'm going to do another theoretical question. This one's going to go a little bit quicker because this one does kind of involve math, but it's a little bit different. Let's say that you are on a theoretical planet, and on this theoretical planet, it had twice the mass of the Earth, and it had, but because it was twice the amount of the Earth, it was also twice the radius of the Earth as well too. Okay, so if you weighed 500 newtons on Earth, what would you weigh on this mystery planet? Okay, so 500 newtons would be your force, your Earth weight. Okay, and two and twos cancel out, so you'd weigh the same. That is not correct. Yeah, and I think about it. Like if you weighed the same, it makes sense that they might cancel out, but we have to analyze this. We have to think deeper. We have to think deeper than this. Okay, because your initial instinct was that this mass is the weight's going to be the same. Um, but I encourage us to look at Newton's universal law of gravitation, and Newton's universal law of gravitation tells us that the force of gravity on an object is going to be equal to big G, which doesn't change, right? Little m, big M, over the radius or the distance squared. Now, two of these things changed in this problem. In this problem, we went to a mystery planet where the mass changed and the radius of the planet also changed. So the big two things that are happening here is the mass and the radius squared, and these two things are not equal in terms of their effect on each other. The distance away from the object makes a much greater effect than the actual mass of the object itself, okay? Because it's related to the mass of the planet and the distance from the center of mass of the planet squared, okay? Even more squared. Has to be that way. Okay, so here's how I normally do this. Okay, I ignore everything else that's constant. So I look at this expression and I'm like, G's not going to change. The mass of the person's not going to change. This is the only part that I have to worry about, this m and this r squared. Okay, so between this, it's 2m and divided by 2r squared, which means that this is really 2 over 4, which is 1/2. You're going to weigh half as much. Okay, so on a planet that's twice as massive and twice as big, you are going to weigh 250 newtons. Okay. did I were you expecting it to be more? Okay, I mean that's fair because it was twice as massive, right? If it was twice as massive, our immediate thought process is at least equal or greater. But since the distance has more effect, I will explain Jupiter to you. How do you want me to explain Jupiter to you? How do you weigh more? Okay, well let's go with it. What is the mass of Jupiter? Let's Google this because this is totally a question. What is the mass of Jupiter? It is, let's just assume that we don't sink through it. Yeah, let's just assume that we don't sink through it. So like let's look at the case for Jupiter. I can't spell Jupiter, but whatever. What's the mass of Jupiter? I'll call it MJ for Michael Jordan. I mean mass of Jupiter. What is Yeah, definitely a Google question. But why doesn't Google tell you? Google has to tell you. You just probably said it wrong. Hey Google, what's Google? Why are you showing it to me? Tell me what it is. 1.89. How about 1.9 then? 1.9 times 10 to the 27th kilograms. Okay. And then what's the radius? I'll call that RJ. What's the radius of Jupiter? Miles? What are you? What class is this? KMS. I need this in meters. KMS system. 69,000. Did you say 811? Oh my God. 69 million meters. Okay, so that's 69 million meters. Do you really want to write it like that? How about scientific notation? 6.9 1 2 3 4 5 6 7. 6.9 times 10 to the 7th meters. Okay. So we should be able to find the force of gravity using using the radius and the mass. Okay. So we can use this to actually find out how this relates to our the Earth. So let's look at the Earth, and we're going to have to use these as comparisons between them. What is the mass of the Earth? Me. Mass of the Earth, which is like what? 5.9 times 10 to the 24th kilograms. I think we already looked that one up. And the radius of the Earth, we already looked that one up too. What is that? 6 times 10 to the 6th meters? I might need to 6.3 times 10 to the 6th? Yeah, just go back one page and look it up. Okay, so 6.37. All right. Now, remember, whenever we're talking about gravity, the mass, if we took a person and we went over to the moon, the mass of the, or to the Earth or Jupiter, the mass of the person doesn't change, and the gravitational constant doesn't change either. So the only really things that we're looking for is we're focusing on the mass of the planet and the radius squared. And we have the mass of the planet versus the radius squared down here. So we can use these to form like ratios. So if I were to look at the Earth and I said, 5.9 times 10 to the 24th divided by 6.37 times 10 to the 6th squared, that's going to give me a number. What is that number? Yeah. And then the other one for Jupiter, that's going to give you 1.9 times 10 to the 27th divided by 6.9 times 10 to the 7th squared. These two numbers are going to give you a relation on how much gravity is compared to the Earth. And this is really, honestly, this is going to explain, like, look at the number difference. The radius of Jupiter only goes up by about 10 times, 6.37 to 6.9, but the mass of Jupiter goes up from 24 to 27 1,000 times. So even though if you're going up 10 times as much, 10 times 10 is 100 down here. So you'd be dividing by 100, but you would be multiplying by 1,000. So that means that the gravitational force on Jupiter is going to be a lot stronger. Even if I don't even calculate the ratios, I can just see it by the numbers right there that Jupiter is going to be a greater gravitational force value. Okay, just by looking at the exponents. Um, so do we want to calculate the numbers out? Because I'm pretty sure one of them is going to be about 10 times greater than the other. Earth is 1.45. Okay. Oh God. Okay. 1.45 times 10 to the 11th. This may not be a very helpful ratio then. 1.45 times 10 to the 11th. And then that one. Okay. So whatever these two numbers divided by each other is, that's how many times greater Jupiter's gravitational force is than Earth's. Okay. So obviously, and we can see like 3.9 is greater than 1.45. So it's greater. Okay. So instead of 9.8 meters per second, it's going to be somewhere around 30. That actually makes, yeah, I think that's about right. 2 point, do what? 2.68. Okay, 2.68 times greater than Earth on Jupiter. Okay. We are totally out of time. So that was fun talking about planets and traumatizing you guys.